Welcome back. This is Mrs. Rubright with Algebra 1 Honors. Today's lesson is 3.5, and it's scatter plots and trend lines. So we're going to go over some correlation, lines of fit, lines of best fit, and predictions. All right, so the degree to which a scatter plot shows a linear pattern is an indicator of the strength of a correlation, right? The strength of a correlation between the two variables. Mathematicians have defined a measure of the direction and magnitude of the correlation. This measure is called the correlation coefficient and is denoted by R. When the points of the scatter plot all lie on a line that is not horizontal, R is the value of 1. If it rises from left to right, and a value of -1 if the line falls from left to right. So it's 1 versus -1. So it's rising. That's a 1, -1. Okay, this is a very strong correlation. So basically, the correlation is, if you're doing like a line of best fit, it's basically the distance here, all four of these distances has to equal these distances. So you're basically having an equal distance between the ones on the left and the ones on the right of the line. Does that make sense? So you're trying to make the line where it's, kind of smack in the middle of where everything would kind of meet up. So these distances here should be pretty much the same as adding those three distances. Okay? So if you're looking here, these dots are kind of all over the place, right? So it's like, do I put my line of best fit here? Do I put it here? It's kind of a weaker correlation. So it's closer to 0.5 than to 0 or 1. All right, so this correlation, you can still kind of see that it's a positive correlation, but it's kind of, it's not tight. It's not close to that line, where these are very compact, very close to the line. These are more spread out. So this has a weaker correlation. This one is a weaker correlation of probably about -0.5. So looking over here, this just looks like a bunch of acne. I can't really tell if I'm supposed to make my line positive or negative. I really can't draw a line of best fit, right? It's really hard to here. So the value of R is close to 0 because the points do not show any linear pattern. Yeah, see, I really don't know where to put the line because I don't really have a line of best fit. There's no positive or negative trend here. There's no correlation. It's just a bunch of random dots. If the variable x and y have a strong positive correlation, what generally happens to the y as x increases? What if x and y have a strong negative correlation? So if they have a strong positive correlation, then y increases as x increases, right? It's going up. If it has a strong negative correlation, then y decreases as x increases. Make sense? All right, so the table lists the latitude of the average annual temperatures for various cities in the northern hemisphere. Describe the correlation and estimate the correlation coefficient. All right, so we're going to make a scatter plot. So the data pair for Bangkok has been plotted. So we already did Bangkok, so now we need to do Egypt. All right, so we have 30.1, comma 71.4. $51.5, 51.8, 55.8, 39.4, 28.6, 77. 35.7, 58.1. 49.2, 49.6. All right, so I plotted all those points. Describe the correlation and estimate the correlation coefficient. Because the plotted points appear to lie very close to a line that slants downward from left to right, the scatter plot shows a strong negative correlation. So the correlation coefficient is close to -1. Make sense? Mexico City, Mexico is a latitude of 19.4 degrees north and has an average annual temperature of 60.8. If you include this data pair in the data set, how will it affect the correlation and why? 19.4, 60.8. 19.4, 60.8. Sorry, ignore that. That was from your quiz. All right, so if we have a point here, what's it going to do? It's going to bring, right, if I add a point here, it would weaken the correlation because the data point is not as close to the line as the other points are, right? It's going to bring down that line. It's going to weaken that correlation. It would weaken the correlation because the data point is not close to the line that the other points are near. Correlation and causation. In the preceding example, you would expect that a city's latitude has an effect on the city's average annual temperature. While it does, there are other factors that contribute to a city's weather, such as whether a city is located on the coast or inland. A common error when interpreting data is confusing correlation and causation. If correlation exists between two variables, this does not necessarily mean that one variable causes the other. When one variable increases, the other variable may increase or decrease as a result of the other variables not being considered. Such variables are sometimes called lurking variables. All right, so it says read the article. Decide whether correlation implies causation in this case. Brains, oh my goodness. How do I say that? Image something connected to social behavior. Does anyone know how to pronounce that? Sure. An almond-shaped part of the brain called the amygdala, something like that, has long been, just A, has long been known as to play a role in people's emotional states. Now scientists studying the A have discovered a connection between its size and the size of a person's social network. The scientists use a brain scanner to determine the size of the A in the brains of 58 adults. They also give each person a survey that measures the size of the person's social network. Their analysis of the data found that there is a correlation between the two. People with larger A's tend to have larger social networks. So if you have that larger part of that brain, of your brain, then you have a larger social network. So identify the two variables that scientists correlated. Was the correlation positive or negative? Anybody? So wouldn't it be the size of the A, and then the size of their social network, right? And they found a positive correlation. Decide whether correlation implies causation in this case. Explain your reasoning. So causation is possible, but which variable controls the other is not known. It's possible that having a larger A might cause a person to have a larger social network. Or it could be the opposite, right? Or it might be that the size of the network causes that portion of their brain to grow. Or the larger social network may cause that portion of the person's brain to grow. Right? However, neither variable can be in control because a lurking variable may cause both the social network and that portion of the brain to grow. So you might have a hidden issue that actually is causing both of them to go up. So we really don't know for sure. All right. So suppose scientists study a group of people over time and find that those who increase the size of their social networks also had an increase in the size of their portion of their brain. Does this result establish a cause and effect relationship? Explain. So no, it's still not possible to determine which variable controls the other to rule out, and you can't rule out the possibility of a lurking variable, right? So no, it's not possible to know which one is causing the other, or if there is a lurking variable. Right? We don't know for sure. When paired numerical data have a strong positive or negative correlation, you can find a linear model for the data. The process is called fitting a line to the data or finding a line of best fit for the data. So finding a line of best fit for the data. The table lists the median age of females living in the United States based on the results of the U.S. Census over the past few decades. Determine whether a linear model is responsible for the data. If so, find a linear model for the data. Identify the independent and dependent variables and specify how you would represent them. So what's independent? So this is your y, this is your x, right? Time is normally going to be on your x-axis, right? So that's your input, your x, your y, your output. This is your domain. This is your range. This is your independent variable. This is your dependent variable, right? The independent variable is time, so use the variable t rather than let t be the values of 1970, 1980, and so on. Define t as the number of years since 1970. So we're doing the number of years since 1970. So that's 0 years since 1970. That's 10 years. That's 20 years. That's 30 years, right? That's 40 years. Do you guys get what I'm saying? So our t's are going to be 0, 10, 20, 30, 40. The dependent variable is the median age of females. Although you could simply use the variable a, we can use f as a subscript to remind yourself that only median female ages are being considered. So the dependent variable is a to the f, right? So what do we have? We have 29.2, 31.3, 34.0, 36.5, 38.2. So 0, 29, so this is going by what? 25, 30, 35, 40, 45? Okay. So 0, 29.2, 10, this is going 10, 20, 30, 40, 50. So 10, 31, 20, 34, 30, 36, 40, 38. Wow, that looks so linear. Draw a line of best fit on the scatter plot. Right? Using a ruler, draw a line that passes as close as possible to the plotted points. Your line does not necessarily have to pass through any of the points, but you should try to balance the points above and below the line. Mine looks so linear, it's like crazy. What type of correlation does this does this have? It's definitely a positive correlation, right? It's a strong positive. Before you place a ruler on the scatter plot, draw the line of best fit. You may have thought that the plotted points were perfectly linear. How does this table tell you that they are not? So if you actually did like your slope between between the points, it doesn't have like you're changing y over your change in x is not going to be perfect. So it doesn't have like a perfect rise over run. So it's not a perfect linear, but it looks very close to it. Okay? So if you put them into the slope formula, you will see it's not a constant rate of change. Making predictions. A linear model establishes the dependent variable as a linear function of the independent variable. You can use the function to make predictions. The accuracy of the prediction depends not only on the model's goodness of fit, but also on the value of the independent variable for which you're making the prediction. A model's domain is determined by the least and greatest values of the independent variable found in the data set. For instance, the least and greatest t-values for the median age data are 0 for 1970 and 40 for 2010. So the domain of the model for the data would be t such that 0 is less than t, which is less than 40. Making a prediction using the value of the independent variable from within the model's domain is called interpolation. Making the prediction using a value from the outside of the domain is extrapolation. So within the domain, outside of the domain. As you might expect, you can find greater confidence in an interpolation rather than extrapolation. All right, so a linear equation that models the data from the previous example is A sub f equals 0.25t plus 29. Use this model to predict the median age of females in 1995 and in 2015. Identify each prediction as an interpolation or an extrapolation. All right, so we still have 3 minutes. Okay. To make a prediction about 1995, let t equal, what are we going to let t equal? In 1995, what are we going to let t equal? I just heard it. 0.25, it's actually 25. All right, 25. So look, it says to predict the median age in 95 and 2005. So why did I go with t equals 25? Anybody? What?
Is it middle value for the 2 years?
So it says for 1995, so let's go, okay, so they're doing 0.25 times t, right? Plus 29. Did they give me any other details? Okay, so they're using 40 for 2010. They're using 0 for 1970. So from 1970 to 1995 is how many years longer? 25 years longer. So if it's 0 for 1970, it's all this is part of the question. And that's why it was confusing, because they put part of the question above the question. So it's 25 years since then. So we add 25 in there, and we get approximately 35.3. Because the t-value falls within the model's domain, the prediction is interpolation. Make sense?
Would you like to?
Siri's answering us. I don't know why. Nobody touched her. All right, so then for B, to make a prediction about 2015. So how far after 1970 is 2015? 45 years later, right? So we're going to plug in a 45. And when we do that, we get 40.3. So does 40.3, wait 1 second guys, does 40.3 fall within this range?
No.
No, it does not. So it falls outside of the range, so it's a extrapolation. Okay, do you guys see the range is up here? So it's all about, does it fall inside or outside of that range? So that is actually everything. So you guys are going to do your homework on 155 and 156. Have a great day.